exercise 4 in your problem set 1 that I think we did this in the class, but then my software didn't work and I didn't have the sound in the recording, so we'll record it again now. So let's state what's given here for us to us. So this is class 1 exercise 4, and we're told to do a hypothesis testing on the model coefficient estimate from exercise 3. So let's write this down. So this is test score, predicted values of test score 524 minus 582 class size, basically. That's class size, and we are given R squared, we are given SER for this model, but we don't need any of this. So we will now state the hypothesis that we need to test. It's that beta 1 equals 0. Alternative is a two-sided hypothesis that beta 1 is not equal to 0. Right, so that looks like a heart, so that's why it is. Now, what do we need to do here? Now basically we need to test if this is 0. This is beta 1 hat, estimated coefficient, using the sample that we have. And the idea with the hypothesis testing is when you have the 0 is whether the effect of this variable on test scores is significant. Basically, is this effect is significantly different from 0? That's what we want to test now. Now, how do we test this? Now, for hypothesis testing, we need a little bit of a strong assumption. And if you remember, we said that the expected value, sorry, not expected value, let me go back. We said that the errors are distributed normally with mean 0 and variance 1. And if that's true, if this assumption is true, then these also are, the betas also are distributed normally or approximately normally in large samples. Now, given this assumption, we can test using test this hypothesis using the usual z-test. I think everyone remembers this at this stage, so let's do this. Now let's assume that we have this distribution. Let's assume this is my normal distribution. So this is basically the sampling distribution of the beta hats. These are beta hats, and we know that the expected value of this of this beta 1 hat is actually the population beta 1. This is beta 1, sorry, this is beta 1. So expected values are mu, so this should be this value here. Right in the middle, this is the average value, right? Now, using our sample, we estimated this value, minus 5.82. Given that we hypothesized this is 0, it must be somewhere to the right, to the left of this. So this is somewhere here. This is somewhere there. This value falls right here. So basically, if you take another sample and run a regression, and your model may give you the coefficient estimate of a positive value, maybe it's somewhere here, somewhere there, somewhere, basically somewhere here. Basically, each of them have the probability of occurrence, and probability of occurrence in continuous distribution is this at the area of under the curve to the left, usually, of this value occurring. Now the question is, we want to do hypothesis testing that the beta 1 population average value is 0, but we've got this value well, it appears to be non-zero, but how far is this from 0? This is the distance we want to find out. How far is this? And if you remember, this distance is measured in standard deviations. So we need to find the standard deviation, the amount of standard deviation here that this guy lies here. Now for that we need to transform this into standard normal distribution. That's exactly the same. Assume that this distribution is exactly the same as this, the one above, just with 0 here and everything here is now z's. And this value will have some z1 value here, right here, this value. So it's the distance basically from 0. And remember that z's are, if we assume we want to calculate z1, let's say, in that case it will be minus 5.82 minus beta 1 over the standard deviation of the beta 1 hat. Sorry, beta 1, this beta population standard deviation. But we don't have this. What we have is, we have the standard error of the regression coefficient list. We can replace this with this. Now if we do that, this will not be z, but it will be t. So this will be t. That's why we usually call this a t-stat. We calculate the t-stat. So t equals then minus 5.82 minus 0, this is the beta 1, I hypothesize 0 here, over standard error of regression. Now this is given, actually, it's given, and it's standard error of regression coefficient, it's in your problem set, is 2.21. I just didn't put it earlier when I stated the exam. Exam so this is 2.21. What value we get is this, minus 2.63. This is the t-stat. That's why we call it t-stats usually. The reason is because of the standard error here. Standard deviation being replaced by the standard error of the beta 1 hat. Now, so this is a t value, and the standard basically distance between them is 2.63. 2.63. Another thing now, how do we still don't know whether this is sufficiently, this value is sufficiently away from 0. We still don't know that. Now let me clean this quickly. I think there's something else there that I need to go over again. Right, very up. Okay, now let me go back to my pen. So I'll just plot the original, not original with the t. This is our 0 mean. Now we still don't know whether this is significantly different from 0. This value is significantly different from 0. One thing we know is that we are told to test the hypothesis at the 5% level, right? At the 5% level. And we also told this is a two-sided, yeah, not equal to 0. We don't know the direction of the hypothesis, alternative hypothesis here. So we are not told whether the beta 1 is greater. We are not told we have to test smaller than beta 1, a value smaller, hypothesized value smaller than beta 1. So what we do is we now split this by 2. So we need to test now at the 2.5% level. Oops. So this is basically 2.5%. Now, in that case, if you look up the t-table, you will see that in large samples, t is equal to z basically. T values are equal to z values in large samples. And let's assume that is the case. In that case, at the 5% level, when we're looking at the two-sided hypothesis testing, t values are 1.96. These are critical values from t-table, and minus 1.96, and that's because we have the two tails, because we have looking at the non-directional test. We won't know whether this is greater or small. We are only interested in whether it is not equal to 0. That's what we are. So this is our alternative hypothesis, and that's what we incline towards usually. So anything that lies beyond this point and beyond this point is in the rejection region, and you know this from your econometrics 1. So our t actual that we calculated is in models is greater than the t critical. What's the decision? Well, we have now enough evidence, or strong evidence, that at 5% level the coefficient estimate here is significantly different from 0. In other words, the estimate here, or this estimator basically, is estimated or used in the sample which comes from a population with non-zero mean. So the population, sample from which we estimated this value comes from the sample that we calculated, which we used to calculate this value, comes from a population which has a non-zero mean. But we hypothesize that it may have come from a population with a zero mean. So remember we have the population coefficient. So we have population classes here. And we picked up some sample and estimated this thing. And we hypothesized that the actual population mean is zero. This is zero. That was our hypothesis. It turns out, given the beta coefficient, and if the hypothesis is true, then this is not population with a mean zero. This whole population is not doesn't have the mean value of zero. So in that case, we simply conclude that the effect of class size on test scores is significant at 5%. Now what about at 1%, which is also a requirement? Well, again, we divide this by 2 because it's two-sided. You get 0.005. So, and the t critical for these values, which somewhere here will be 2.58, and minus somewhere here minus 2.58. And again, our actual value lies beyond this point, and somewhere here is our 2.63, the actual value, t actual. This is t actual that we calculated. So we again reject that null hypothesis. So at the 1% level, so the decision is that we have even stronger evidence against null hypothesis, basically. Yeah. So that's it with hypothesis testing, basically. Now that should be fine. Let me switch finish this video recording. I'll try to make them shorter videos.